So now in the last video we used a bipolar junction transistor. This one's a PNP bipolar junction transistor. Last video we used an NPN bipolar junction transistor, the 2N2222. This one we're going to make basically the same circuit but with a PNP transistor. So this is the 2N2907. It has, for the most part, about the same characteristics as the 2N2222. So even amongst different bipolar junction transistors, they have different strengths and weaknesses. So these are more power transistors. They handle more power. There's other transistors like the 2N3904, the NPN type, and the 2N3906 that turn on and off faster, and they don't handle as much power. So there's different strength and weaknesses two-way. And so in any case, we're going to make basically the same circuit we did, which we have 18 volts at the rail. We're going to drop that down to about 9 volts with the Zener diode, and we're going to use a high value resistor to set the current through the Zener diode, so it won't be able to power a load very well at that voltage, but we're going to use the transistor to amplify that. So in any case, let's get to it. So the Zener diode, since we're using a PNP transistor instead of an NPN transistor, first thing we're going to do, we're going to put it on the other side of the power rail than what we had before. So with the NPN transistor, the Zener diode went to the negative rail. In the PNP transistor, we're going to go to the positive rail. And so we still have to reverse bias it. So we want the black stripe towards the positive side, and we will put this jumper one row up, and there we go. So we have the Zener diode there. So now we need to limit current, which is actually going to be a negative current, the way that we're going to look at this circuit. So I'm going to use a high value, relatively high value resistor here, and we're going to go to the negative rail right there. And we could put the resistor on top and the diode towards the bottom, but doesn't matter as long as they go to the right rail. So there we go. So what we have here, okay, the bench power supply is already on. I'm going to zoom back. I actually started shooting this before I forgot to zoom back to the multimeter. We are going to measure voltages right now. So bench power supply is set for 10 volts, and as you, or 18 volts, sorry. And as you can see, there's 18 volts right there. At this point now, we don't have the 9.2 something volts we expect, because now we're actually going to have our ground to the positive rail. And now when we check it, now you see it's about the 9.2 volts, but it's negative. So we have a negative voltage because PNP transistor uses opposite polarities of the NPN bipolar junction transistor. So the pin layout is the same. So when we look at it, this is a 2N transistor, 2N2907, and all the ones I've come across before, of course it's best to always check the data sheet. If it begins with 2N, whether it's NPN or PNP, we have the emitter to the left, the base in the middle, and the collector to the right. So I'm going to keep turning it a little this way, and we're going to use a jumper to go across here, and that's where the base will connect, but it will go directly to the diode right there to get the voltage to the base of the transistor. So that is middle pin. So we'll plug that in right there, and we are good to go. You can see that pretty good right there. So I will turn the meter off. We already know we have that voltage at that point, which we're considering the red rail ground now, and so we consider the voltage negative 9 volts in relationship to the red rail. So with the NPN transistor, we put the collector to the positive rail directly, because this is going to be an emitter follower. We just want the voltage at the emitter. We're not going to control the current. Current is going to just automatically be controlled by the transistor in order to keep the voltage at the emitter to what we set it to, minus the base to emitter drop. So we have this jumper to the negative rail to the collector. So, keeping with the reverse polarities, we are going to grab a 2.2 kilo ohm resistor, so 2,200 ohms, and we're going to put it to the positive rail, because with the NPN transistor we put it to the negative rail. And there we go. So now we should have negative 9.2 volts minus the 0.7 volt base to emitter drop. And so we will first go to ground, the positive rail there, or we could go up to this jumper. Yeah, you can see that on camera just fine. And so we still got the negative 9.2 volts right there. Let's get that V. There we go. Negative 9.18, and then 0.7 lower than that. Since it's negative, it would actually be a little bit higher, but to make the math easier, lower than 9.18 by 0.7 is about 8.5. So we should have about negative 8.5. And there, you can see it right there. So, the reason why we're doing this, just like with the NPN transistor, so now the Zener diode is the negative side of the circuit. We can plug this here, and this will actually sap current away from the transistor. We can pop the transistor out for now, and we will take a 470 ohm resistor and put it to the positive rail, because the output is negative. The LED is not very bright, as you can see there. So let's pop the transistor back in. So we already saw that there was 9 volts before, and negative 9 volts, and now it's obviously lost a lot of that energy, and that's because I'm using a high value capacitor, but I did that on purpose to prove a point. We don't want to have to depend on current from the Zener diode and the resistor. We want a transistor to handle all the current just looking at the voltage. So we will pop this out, and wiring it the same way at the emitter of the transistor, we're going to put the short lead, the cathode, to where the emitter is, because we already saw that is where the voltage is, where we set it. So long lead, the anode, is down here. Short lead, the cathode, is to the emitter. And we're going to grab this 470 ohm resistor. Since it is 9 volts in the negative, 470 ohms going to the positive rail now, we'll be able to limit the current enough to protect both the LED, keep it below 20 milliamps of current. You can see it is a lot brighter. Even though we're using the same resistor and the same voltage, when we stuck it on this end, it sucked the voltage down too much, more than the resistor and Zener can handle. Now, the transistor is handling all the current. We just have a program set there, a voltage, I should say, set at the emitter, and the transistor is providing whatever current it needs to hold that voltage, because it's wired as an emitter follower. And we can look at that. So again, our ground is the positive rail now, because it's an NPN transistor. We're dealing with opposite polarities. Of course, we can call ground wherever we want, but with an NPN transistor, it's generally the negative rail. And then with the PNP transistor, it usually goes to a halfway point called ground, zero reference point, and then it deals with lower voltages. But we don't have a halfway point where there's a more positive side of the circuit. We are just going to go to the positive rail, call that our ground. But you can see here at the emitter there, we have 8.42 volts. So again, it's about the, okay, I wanted the black probe up there. So we got the negative 9 volts there at the Zener diode, and then we come over to the emitter, and it's about in the range of about 0.7 volts less. And so we want to fix that. So we did this with the NPN transistor. I'm going to I'm going to turn the power off. If I accidentally did this when I was testing out the circuit before. If I yank out the Zener diode, you'll see the LED get brighter. You may have noticed it got brighter. We are putting too much current through that LED and that resistor right there. They were both probably starting to overheat, and so You don't want to do that. So we're going to turn the power off before we make an adjustment. We could also yank the resistor out first. That would have kept the transistor fully off. But we're going to take out the Zener diode and grab a rectifier diode. So we're going to forward bias the rectifier diode. So the side we're going to connect to the Zener diode that goes to the positive rail. It's going to be the anode, the side without the stripe. The cathode, the side with the stripe, going to go to the resistor, which goes to the negative rail right there. And what we will see when we turn the power supply on. So again, before I forget, ground right now is the positive rail. Now we have about 0.7 volts, actually about 0.5 volts. We looked at this in the last video. Because there's such low current going, it's actually raising it about 0.5 volts. But in any case, this number works really good for us, 9.72 volts, because when we come to the emitter of the transistor, it loses about 0.7 of that volts, so it drops from negative 9.7 to basically negative 9 right here. So we have 9 volts across the LED and the resistor here. And so as far as the transistor is concerned, though, it's emitting a negative 9 volts because it's going to the positive rail. So it's 9 volts lower than the other side of the load. That is why we are looking at it this way. So, in any case, this was just kind of a practice, step-by-step build of circuit fragments I covered. I did a few videos on the Zener diode by itself, and I've done rectifier diodes before. This is actually a 1N4148, and as I said with other semiconductors, the transistors, some of them are better at some things than others. So normally I use a 1N4001, which is in black plastic, and that handles higher current, up to like 1 amp. And this one is intended more for 200 milliamps of current with alternating current, and so half the time it's off even, but even then it's lower current, and at DC, just steady DC, up to 300 milliamps of current. Of course, that's absolute maximum. You keep it below that, and so these handle a lot less current, but they can turn on and off a lot faster. So higher frequencies, these 1N4148s will work better according to the manufacturer. So I don't do high frequency stuff, so I can't really prove that yet, but that's the main takeaway. Generally, the reason why you use different components, they have different strengths and weaknesses, even though basically they are the same component. Maybe it is how much current and power they can handle, maybe it is how fast they can turn on and off, or whatnot, or other things that will influence one circuit but not another, or help one circuit and hurt another. So, in any case, this video is running kind of long, but hopefully you still enjoyed it. Thanks for watching, and I will see you in the next one.